In C.7, we're going to explain the relationship between Graham's law of effusion and the kinetic theory, and the solution of problems on the relative rate of effusion using Graham's law. Let's start off with a picture of effusion. So here we have essentially two compartments of a container, one that contains particles, a barrier that has a pinhole, and then the other side has a lower concentration. So what will happen naturally through diffusion is you want to go from high concentration, low concentration. The idea with the pinhole here is that essentially these particles have to be traveling at exactly the right angle to pass through. And if you were to try and take a look at what happens, it's the rate at which they actually pass through the pinhole. So the lighter particles tend to effuse faster than the heavier ones. And that's because if we take a look at recalling from our unit in kinetics, if two samples have the same temperature, it means the particles have the same kinetic energy. So if they have the same kinetic energy, well, what that essentially means is this. If we break down what kinetic energy is made from, it's made from mass and velocity. So, for example, if you have a heavier particle, what will happen is, if that heavy particle has to have the same energy, then it must be moving at a slower velocity. So heavier particles will effuse slower because they're moving at a slower speed compared to a lighter particle, which will have to move at a higher speed to have the same kinetic energy. So looking at all this, we can derive and cancel out different materials until we arrive to the final law, which is this one, which basically says the ratio of the velocity of one of your molecules to the velocity of another one of your molecules is equal or proportional to the time that each one would take inversely, which is equal also to the square root of their molar masses compared to each other. So let's see what that looks like in an example. So using uranium-235 and 238 enrichment as an example, again going back to our unit on nuclear power and the fact that we can use diffusion to enrich uranium-235, what we have here again are these sort of pinholes. We have a high concentration of uranium-238 to 235 naturally. And what will happen is, since 235 is lighter, it will effuse through the barrier faster, and we end up with one stream with more enriched uranium-235. So here we say determine the relative times for the same amount of hexafluorides, which is what uranium is connected to make it gaseous, of the two isotopes of uranium to diffuse. So the first thing you want to do is you want to find the molar mass. So you take uraniums plus 6 fluorines, and you get 349 for uranium-235, and you get 352 for uranium-238. So we use that formula, knowing that the ratio will be equal to the square root of the mass of A of uranium-238 over the mass of B, 235. So you plug that in your calculator and you get 1.004. In other words, uranium-238 will effuse at a rate of 1.004 times the rate of uranium-235, which is actually not very much. And so since it's not very much, we usually have to run this process several times, where we'll enrich it and then run it through again, enrich it more, until we can actually get a sample that is enriched enough, about 3.5% for nuclear power. And if you want a nuclear bomb, that's 90%. So you have to really repeat this process or combine it with centrifugation, which is another way.